Hi, welcome back. Welcome to lesson 7, Logistic Regression. Logistic regression is a classifier. And before we jump into logistic regression, I want to give you an overview of what we've seen up to now. We've looked at 3 classifiers. The first one was k-nearest neighbors. And what does k-nearest neighbors do? Well, it says that similar points have similar labels. But we've seen that there's an issue because in high dimensions we have the curse of dimensionality. Why is that an issue? Well, similarity here, the similarity measure here is distance. And in very high dimensions, distance loses its meaning. In high dimensions, all points are far from each other. So that was the issue here. Then we looked at perceptron. Remember, perceptron is the simplest form of a neural network. And we had an algorithm. And the algorithm would converge, so would find a hyperplane that separates the data. So y is 0 one hand, y is 1 on the other hand. But it can only separate the data when the data is linearly separable. If the data is not linearly separable, then the perceptron will not converge. And we've seen an example here. The XOR example is one that perceptron cannot solve. And then we looked at naive Bayes. And what's naive Bayes? Well, it's a quick and dirty algorithm. And basically, instead of separating classes, it separates distributions. And there is a hyperplane when we assume that the distribution is multinomial. There is a hyperplane that separates the distributions, not the data. Okay? Basically, once you have the distributions, you can forget about the data. Today we're going to look at logistic regression, and then next few lessons we're going to look at support vector machines, decision trees, and neural networks. Just want to remind you what the goal of classification is. So we have a data set. This is a training data. This is a training data. And this data is drawn from a distribution that we don't know. So given X, what is the label? That distribution we don't know. And that's the goal in classification in machine learning, is to calculate this. But we've seen that we can estimate distributions by looking at the data. We've looked at maximum likelihood estimation. Basically, it means that given the parameter, what are the parameters that best explain the data? And we've used theta here, but instead of theta, we're going to change by W. W are your weights, are your parameters. And we've always talked about finding the W, so we want to be consistent here. So here you need to make an estimation based on the data. And in terms of probability distributions, there aren't too many. So basically you have Bernoulli in the discrete case, multinomial in the discrete case, you have Gaussian in the continuous case. Basically we're gonna take a look at these distributions primarily. If you don't understand all of this, get back to my statistics refresher. Some of the stuff is explained there as well. What's of course the issue when you try to estimate the parameters by looking at the data? Well, I've illustrated it by giving you this data set. So these are 10 coin flips. And these are head, tail, tail, head, and then 4 times tail. So if we would assume that this is a sequence of Bernoulli trials, we can compute the chance that we have heads. The Bernoulli parameter has P. So the chance of heads is actually your P. Well, we can count it 1, 2, 3, 4 out of 10. it's 40%. So here I illustrate what the issue can be in a naive base. For example, is that your estimation is not accurate, and this will have a result on the performance of the classifier. In this case, how can we solve it? By getting more data. More data will reduce your chances of getting something that's below 50% for heads. We've also seen that if I take this away and I would have started the experiment here, we would have 4 tails in a row. So this would mean that the probability of heads would be 0. And of course this is not acceptable. So that's why we use smoothing. And we have used smoothing in one of the examples during the lesson about base classifier. Now another way to estimate the distribution is map. It's mapping a posterior, and basically you're gonna weigh your likelihood with the prior. So here you have your likelihood. Here I replaced already theta by W, and you multiply it by your prior. And this is of course Bayes' rule. So with this you can find the probability of the weights given the data. Okay, let's move on.